So any questions on 182? It's, as I say, it's very, very similar to the two that we did in class. You even have that point C there that's in a plane. Okay? So be aware of that your vector for point OC is going to be in a given plane is what that's going to be, okay? So basically what you got going on there, you got O, and then you got B out there, and that's one vector. You've got OA going off that way. And then you've got this other one kind of going off this way. Then you got the wind force. And I believe you've got, is there a weight on this one or no?
9,000 meters down.
Oh, thank you. Yeah, 9,000. There we go. And then you've got the wind. And then you've got OC. So this is basically your free body diagram. And that aligns, you know, a lot of those forces, of course, align with the axes. I mean, there's the X, there's the Z, there's the Y. So this thing does look an awful lot like the stuff that we did already. You've got the angles for the wind force, like that and like that, and then up and over like that. And then you've got an angle given for OC. And that angle then is given with the z-axis like that. Have a look at those dashed lines and, you know, consider the meaning of that. That dashed line is parallel to the x-axis. It comes off the z-axis. Okay. So what you're going to do is find Cartesian vectors. That's step one. Step the second there is build a matrix. The columns are, the forces are in columns. And then the rows will be X, Y, and Z. And really what these are sum of forces, okay? And their sums are zero. So the columns, or excuse me, the rows are just X, Y, and Z. Okay, and then solve the matrix. On this one, you don't need to do a formal matrix solution. You could, I don't know what the right word for it is, cherry pick, you know. What's that?
Plug and chug.
Plug and chug, yeah, okay, there's different words for it, yeah. Okay, so, you know, it isn't like you got to do a fancy matrix solution on this one. I'll get this up in Moodle. I'll post some intermediate answers if you kind of check and see how you're doing. I don't know, maybe that'll be something I could do for you. I don't want to, but I want you to work through one of these independently, okay? And this is the one, but if there's questions, I'll certainly take them. Okay. All right. So there you go.
Is that dash line the universal sign for it being parallel with X?
Yeah, I guess you could say that. I mean, I'm always hesitant to make universal statements like that because I've kind of built this over the years and I've not been completely consistent on it, if you know what I mean. But yeah, my general convention now is that dash line parallel to an axis means a dimension going, it's a dimension line. And it means starting at the z-axis in this case and going back. I think it's at the x direction, is that right?
Yeah.
Yeah, okay, yeah, that's the meaning of that. Now, I'm pretty consistent with that, but I might have some old homework problems where I forgot to do it. Yeah.
Okay, so when you see get Cartesian vector coordinates for like A, it's just going to be 0, 0 for the y and z, and then just the force is the.
Yeah, I guess, yeah, this, when I say find Cartesian vectors, Cartesian means x, y, z.
Okay.
That's all
so
I mean.
If I use the variable for the force of A.
Yeah.
Okay.
I mean, yeah, I'll even give you FA. It's just 0 minus FA 0 and so on.
Yeah, that's what I had.
Yeah, that's all.
That's what I was doing right.
And you write that down, you're done. I mean, there's nothing else required to generate that. You can just see that one. All right. So we good with that? Other questions? Yes, sir. All right. All right, I got answer blanks down at the bottom of that, and that's an example of one I've written up for you. I don't even think that's in the regular pages. It's on page 6A, I think. And it's just written up and ready to go. So, and I've got the answers for it down below. Oh, I don't think I even asked for vector answers on that, just magnitudes. So you can just fill in the magnitudes down there, okay? All right. Other questions on that business? Nope. All right. There we go. So that's due tomorrow. That's the only one that's due tomorrow. Yeah, that's good. All right, and I guess we're off to the next one here, okay? Here we go. So what we've been talking about here so far are forces, okay? That's what we've been talking about. So now we're going to get into a different action. There's two actions that we look at when we do statics. One is forces and the other are moments, okay? Now, moments have other, there's a lot of words that describe what we're talking about. Another common one is torque. Let's see. Anything else? Anyone else have a word for this? It's like a twisting action, wrench, kind of a wrenching action. It's a twist, or a twist is really what we're talking about here. So if you look at this motor up here and how it drives the pump, what it's doing is spinning that belt and making the impeller down below on the pump spin. That's what's happening there. So that's referred to, the term we'll use is a moment. But if you like working on cars, you might have used what's called a torque wrench. Okay. Remember replacing a head gasket once, and I got that torque wrench on there, and you're supposed to torque them up a little bit at a time, about 10 psi, or 10 inch-pounds at a time. I got to 10 all the way around, then I got to 20, and I went 20, 20, 20. Oh, this isn't looking good. Aluminum block, stripped the head bolt. That was bad. That's not good. It's just FYI, that's not good when you're putting that gasket on. It was up in Alaska too. It was like 20 below, and it wasn't having fun. I had a mobile mechanic come up with a, what do they call those? Quick taps or what other things?
Easy outs.
Easy outs. Yeah. And he put a tap. He tapped a threaded thing in there for me. A coil, helicoil. That's it. He did that. So yeah, I was happy when I sold that car. That was a good one. All right. So there we go. So here's a moment. Okay, it's a twist or a torque about an axis. Okay. So here's somebody trying to take the jar off of or the lid off a jar. The axis kind of extends through. It's normal to the lid. Okay, that's the axis that torque is being applied about. Okay. Now there's common ways to do this. Probably the most common way that people think about with this is you take a force and you offset the force from the axis. So the axis is coming straight out of the lid this time, and the force is being applied at an offset distance. And if you've ever had like lug nuts that are put on too tight, you might really have to push, or if you got a jar on a lid that's too tight or whatever, or a lid on a jar, I should say. What do you do? What are your options here if that ain't going to do it? What are your two options?
Give it something to give you leverage.
Yeah, there's a couple options, right? And the first one is just take the caveman approach and just pull harder, right? Increase the force, right? That's my usual approach. Because it gets me mad, and that gets me more strength so that I can actually get the thing off as easy as it works. All right, so that's one option. But there's a more intelligent option, right? And the more intelligent option is to increase the distance, okay? And that's how you can generate more torque, okay? And if you're doing mechanics, it's called a cheater bar. I use a galvanized pipe, fit it over the end of the wrench, and get more torque that way, okay? Yeah, you can do a lot of things with that, that's true. Okay, so that's the idea here. Okay, so that gets us to this basic formula that moment is force times distance. Okay, and that gets us that torquing action, the twist, whatever it is you want to call it. Okay, so M is moment, F is force, D is distance, and particularly it's the distance perpendicular from the force to the point, okay? So the distance is perpendicular to the force right there, okay? So there's a right angle right there. That's the idea, okay? All right, now we have a 2D sign convention, and it's from the right-hand rule. Counterclockwise positive, clockwise negative. That's the two-dimensional sign convention. And where that comes is the same right-hand rule that generates the XYZ axes, because if you're looking at two dimensions, the moments occur in the XY plane, which means the twist occurs about the Z axis, okay? So if you start thinking in terms of vectors, the twist is any 2D moment is a Z moment, okay? So if you curl your fingers from the X towards the Y, your thumb points in the positive Z. And if you curl your fingers from the X towards the Y, you're curling counterclockwise. So that's where this sign convention comes from. It's kind of an application of that three-dimensional right-hand rule to an XY axis, okay? So a positive moment is clockwise, counterclockwise. Negative moment is clockwise in 2D. All right, so there's a couple little calculations there. That one on the left, 60 pounds times 2 feet. We use pound-feet for our units when we talk about moments. Instead of foot-pounds, we usually use pound-feet. I might get a little sloppy about that, but the convention is force first, distance second. So that'd be positive 120 pound-feet there on the left. On the right, it's clockwise, so it's negative 110 times 0.4, it's negative 44. Okay. So I'm just taking the force times the perpendicular distance to generate the moment. And then if you just, if you have any doubts about this, I've seen different ways to do it. Just put a pencil in your hand and push on it, and that one's going to go counterclockwise for that first one. On the left, if you held a pencil out vertically or horizontally in your hand and push down on it, it'll start to rotate in that fashion counterclockwise. So it's positive, whereas the other one will go clockwise. I've even had people trying to figure out signs on homework problems. They'll actually hold their paper where they've made their sketch. There's a wrench. They'll put their finger right there at the point about which they're taking moments, and then they'll push the paper in the way of the force, and whichever way the paper rotates, that's the sign they'll assign it, okay? So that would be negative, okay? So however, whatever it takes to develop this idea, you can do it, okay? So counterclockwise, positive, clockwise, negative, okay? All right. Now there's a couple other ideas here that are developed. The first is called transmissibility of a force, because what we want is the perpendicular distance. That's what we want. If I were looking at this particular case right here, if I'm going to analyze that force up where it's applied, that's not a perpendicular distance. So I'd have to do some trig or something like that to get the perpendicular distance. What I can do, though, is I can take that force, and when I'm calculating moments, I can apply it anywhere along its line of action. So I can put that force anywhere I want on that line to calculate my moment arm, as it's called. So I'm going 4 meters over and 1 meter back. That's 3 meter distance. I can slide that force and put it down there. 3 meters times the magnitude of that force, and I put the force not quite in the right spot. It should be right about here. Okay. So that moment about A there would be 600 newtons times 3 meters. And again, if you're coming around that way, you would curl like that. That would be counterclockwise, so that's positive. All right. So 1,800 Newton meters. Okay.
Is it convention when you're talking about a moment to include a positive sign? Or can you leave it, and if it's negative, then?
Yeah, okay, yeah, I guess the signs deserve a little bit of discussion. There's different ways to do it. Now, that one there is a positive 120. I put the positive because I'm just introducing the idea, so I wanted the positive in there. You don't need it.
When we were doing it, yeah, it can just be a 120, and that's a positive.
The lack of a positive implies it is positive. Yeah. Now then a negative can be drawn up as a negative. You can now an unambiguous way to call it out is just put arrows on it. kind of that idiot-proof kind of approach that I like to use. It just helps me. It's going this way, it's going that way. It's quite unambiguous. This does not need a sign because I'm saying it's 44 and it's going clockwise. That's enough to describe what it is. Okay. All right. Okay. Now there's another. So we good with that? Okay, now the other thing is the principle of moments, and that's called, and I always struggle with French because this is a French scientist, Varion, something like that. Bar, to go, Varion, there we go, something like that. Anybody speak French? I had a student who spoke French, native French speaker. She helped me out with that. I used to stumble over that for years. So there we go. And this is a theorem, okay? And what this says is that the moment of a force about a point is equal to the sum of the moments of the force's components about the point, which is kind of a mouthful there, but it's probably better illustrated by example, okay? But that's called Varion's theorem. All right, so, and I don't know if I have these down. They're pretty simple little sketches, so I don't think I put these in your...
We just got a blank.
Yeah, you just got blanks. So, yeah, just put them down somewhere. Let's find the moment about point A. So what's the moment about point A caused by this force? All right, we got that. Got a bit of a sketch there we can work on. Doing all right? So we just got a little bit of a post or something, then we got a rectangle on there, and we're applying that angled force. Notice the 70-degree angle. And we want to find how much of a moment does that cause about point A. So when you look at moments, you have to specify the point about which the moment is taken. In this case, it's point A. Okay? And I might want to do this. Maybe I have to connect these two together. Maybe I got to weld the rod to the plate or something. And I want to know how much of a moment do I have to resist with that connection. That's why I might do this. Okay. I want to know what the effect is of that 8,000 newtons at A. What sort of twist does it cause about A? Okay. All right. Now here's the Varion's thing. Or Varion, I don't know. Okay. Now, if you try and get the perpendicular distance here, you can apply that force about its line of action anywhere you want, but you'd have to do a little bit of geometry here to get that perpendicular distance out there, wouldn't you? Now, you could probably figure it out, but it would be a fair amount of effort, and it would be a little bit difficult to do. But to get the moment, if you want to use the 8,000 Newton force, you got to find that perpendicular distance. That's part of the definition of a moment. The distance is perpendicular to the force. Well, that's kind of a pain to do that. That would be difficult and a little complicated. So a simpler way to do it is to take the force and break it up into x and y components. And this is the theorem here, that you can do this. So what you're going to do here is you're going to find the distance that's perpendicular to each of the components. Okay? And that's easy enough to do because those are x and y components. So perpendicular to the y component, we've got an x distance. Perpendicular to the x component, we got a y distance. And that's all there is to it, okay? And this is a real important concept here in statics. is this idea that what we do, we take stuff and we break it into x's and y's because it's easier to deal with, okay? You notice we're doing this with forces, right? Some of fx and some of fy and all that. We do this, we're doing the same business now. We're getting that force broken up into x and y components, and notice the dimensions on this plate will give us our moment arms. We're good to go. We don't have to do any sort of fancy geometry here or anything, okay? All right, so what I do, I just do a little bit of trigonometry there on the bottom to get to those component vectors. So cosine 70, that's the adjacent side, that's the 2736. Sine 70 is the opposite side, that's the 7518. Okay. And we got those in there. And notice I got arrows on those. The 7518 is down and the 2736 is to the left. And the reason for that is the 8000 is down and to the left. So the components go down and to the left.
When you're calculating the moment at A, do you have to consider the part that's going to the right? Or is it just the part that's going down for your work?
It's down and to the left. I
So you have
mean,
to do two of them?
yeah, you got to do two of them, right? Yeah. Okay.
You just sum them together.
Yep. Yeah, that's the very own theorem. Okay. So what you do, you just do each one separately, and then you add the results together. But pay attention to your signs. Okay. So we got the 7518 is down like that on its line of action. That'll get me a 1.2 meter moment arm. So the y component of force goes with an x moment arm. You need those different directions to get a twisting action is the idea. And then the x component of force uses the y moment arm. Okay? And see, this process is greatly simplified when you break things up into components. Because you get x and y forces. It's very common in your dimensioning to have x and y dimensions. You just combine the x's and the y's together and the y's and the x's together. That's the deal. You do have to watch sign, though, on this. Okay, it's important. Okay. All right, so if you hold a rectangular piece of cardboard on the table, you put your finger at A and you push it this way, that rectangular piece of cardboard would rotate that way. That's clockwise. Okay. Same thing, if you hold a rectangular piece of cardboard, you know, take a Post-it note, or not a Post-it note, but a note card or something, hold it down at A with your finger, just push down on it, push on it to the left there at the top, that's going to come around that way, right? Counterclockwise. So the signs are different. You got to consider that when you sum the two. So it's negative 9022 plus 2462. So the result is negative 6560. And so the net moment there is 6560. So if this were some sort of what I call a pin joint here, just a little it's kind of a raised triangle of metal with a bolt going through it or a rivet that went through the plate, that plate would start to rotate clockwise when okay, if we applied those forces. Now, it's not. There's some sort of solid connection there that will resist that. So it wouldn't happen probably as long as that connection is strong enough to hold it. All right. You okay with that? Oh boy, we'll come back to that. That's a cross product. I don't want to do that right now. Things are kind of, anyway, we'll come back to that. All right, so now you can just add as many components as you got. Okay, let's find the moment about point B. Okay, now notice I've moved where the point is. So same dimensions, same force in the corner. All I've done here is to move the point where we're taking moments about. You can take moments about any point you want, whatever point might be having, you might want to know about. And they'll be different at different points. And also I've added a force down here. Okay. Okay, so just a little different sketch, same basic shape, same force in the upper right-hand corner, just a new spot for the point about which you're taking moments, and an extra force added on the bottom there to the right. So we good with that? Get that sketched up. All right. All right, now you do the same thing. You do the component stuff. So you take the 8,000, you break it up into X and Y components. The 12,000 is already, an X vector, so I don't need to do anything with that. And then I just multiply everything by their respective moment arms. So once you just run that, just take a couple minutes and run the numbers. And just look at the offset moment arms.
So this one gets multiplied by this one. This one gets multiplied by this one.
What's the one on about? Yeah, that 2736, what's the moment arm on that? That just came up, and it's a good point, and that's why I did it this way, because I want you to kind of get that one figured out. We'll go over it, of course, but think about that for just a second. What's the moment on the 2736 moment arm? Yeah, it ain't much, is it? What's going on? It's going right through B, correct? So what's the moment arm?
1.2.
No. Taking moments about B. 0, yeah. Got it? Okay, and just by way of illustrating that, here's a door. Here's the hinges on the door. Right? If you want to know about opening the door, you want the moment about the hinges, right? Now, if you push on the door over there, right? Because you want to maximize the moment arm. Do you push on the hinges? What happens if you push on the hinges? Not much, right? Because you're not generating any moment. See, that's a 0 moment arm. Okay? So you can have 0 moment arms. If you push right on the point, that's a 0 moment arm, and that doesn't cause any moment. So the 2736 has a 0 moment arm. That's the deal with that, okay? It's not generating any torque. It's not causing that thing to twist. It's pushing on it, but it's not making it twist. Okay? And yeah, I just put that in there just for that very purpose to illustrate that. So that's a common question. Everybody okay with that stuff? And just again, remember the signs, so get the proper signs on those things. And then you just add them up. Okay? And this is something to get used to. This is the drill on doing a lot of this 2D statics. You break everything up into X's and Y's, and then you analyze it, both for force and moment. Okay, it's very helpful to do this because you can generate the moments very easily once you get the forces broken up into X and Y's. If you got X and Y dimensions, it's real easy to put everything together. Okay. All right. Everybody getting the sign correct on that 12,000? And like I say, if you got any doubts about that, just use your notebook or whatever the heck you got. Maybe your physics book, you may not be able to move it, but anything else you probably could. You could just put it down, put your finger on the point about which you're taking moments, and push on it. See which way it goes. Can't, no argument there. That'll be very clear to get your sign. Counterclockwise positive, clockwise negative. I guess calculus books are about as bad as physics books, aren't they? You got like one book for all the calculus? You do, okay.
It's like this big.
So you can carry that and physics around with you?
Yeah, and then another one.
Gets you strong. That's good, yeah. All right. Okay, so y'all good with that? So that 2736 goes right through B. It's a 0 moment arm. The 7518, just like before, is clockwise, so that gets a negative sign. And this 12,000, that'll come around that way, right? Counterclockwise, so that gets a positive. Add everything up, you get positive 1778 counterclockwise. Questions on that? All right. Okay. Okay, now I have a question here for you. Now that's a nice rectangular plate. What if we'd done a little some sort of torch or something and cut up that rectangular plate and changed the shape of it? What if we had turned it into this? So instead of a rectangular plate, we had a shape like that. Would that affect the problem, or how would it affect the problem? It wouldn't, yeah. Okay, so that's kind of important concept number 2 today. The first one is this concept of breaking things into X's and Y's. The second concept is don't get faked out by the picture. It can be a bicycle, it can be a plate, it can be, whatever. It can be a person playing soccer, whatever the heck you want to analyze. What we do, we make a diagram, we find the coordinates of the points, and we put the forces there. How those coordinates are connected together is not important in this class because we assume everything is a rigid body, is the term. It doesn't spring or deform or anything. So all I care about is what's the coordinate of this point relative to B. How that connection is made. If it's done with a straight plate across or if it's done with a curved piece of metal, it doesn't make any difference. It just matters where the forces are applied. That's all that matters, okay? All right, so that's a little bit there with moments. Got any questions on that? Okay, another thing too, it doesn't look like I'm going to be here on Friday. I got a meeting I got to go to. Yeah, I think we'll skip Friday, okay? You all okay with that? All right.
It's like no test, I have a test and then I have nothing. It's the best.
All right. So we good with that? So we got this stuff due Monday. I'll see if I can later on today, maybe I'll try and post a couple intermediate answers for 182 if you're interested in those. Okay. Good to go? Good.
I wasn't sure if I was going to head along in the wrong direction. For the 2, because I was just putting since you're with my next one. And that's how I was supposed to, so I was going wrong. So I have like 9 minutes. So it was nice.